Doesn't.
It's a little bit of an interesting I don't know if they're filming properly as well. It's nice journey. Is this another one of these gadgets? They won't take the proposal, therefore they have to do it. Does it also license? Or is it just recorded? It's the microphone in that thing. Yeah, that is So what's your computer work ethic?
Christian, do you know where are the mics? Where is there another mic?
Okay, let me begin by thanking the organizers for the opportunity to present here. It's a great pleasure to talk at IGST. I have been coming all these years, and now I have the opportunity to talk. I will talk about these three papers. Two of the collaborators, Vladimir and Misha, they are here, and I get to know them very well. So I have to begin by saying what these TN things are, TN theories. And to do that, again, I have to go back to Gaiotto in 2009 to explain to us how to obtain a large class that by now is called class S of 4-dimensional n-equal-to conformal theories by quantifying the 16.2,0 theory on the Riemann surface between G and n functions. And then when I have Gn, I label the theory by Gn. So the same way we decompose the Riemann surfaces, spheres with three punctures and cubes, the same way you can understand class by being made by some building blocks that I would call trivial theories. These are the theories that correspond to a sphere with three punctures and color factors, which I use to view the trivials. The trivials that I care about, I will call them TN theories. They are depicted here. They are sphere with three punctures that are labeled by this symmetric Young tableau. And these are being called in the literature full punctures. What you have to know about them is that these theories, they correspond to isolated fixed points. There is no Lagrangian description for them, and they have this SUN to the third global symmetry. Now, this is what I want to tell you, is that we can compute even if there is no Lagrangian description. We can compute the partition function of these theories by using the web diagrams that Benini, Benvenuti, and Tachikawa introduced. And we will use the topological vertex formalism to do that, but, and here there is thing, I will propose a solution for a long-standing problem in mathematical physics, which is to give you the 3-point function of the 3 primaries, 3 generic primaries in total CFT. It will be split into a factor of these two. One transforms covariantly under some transformation that I will introduce, and another part that is invariant. The covariant part will come from these extra straits that here I will say that we have to remove, and the invariant part will really be the partition function. And then, this theory, immediately the moment I make this conjecture, it has the correct answer for n equal to 2, which is the Newville CFT that we all know and love. It has immediately the correct symmetries and the correct zeros. And then I will show you, I will tell you how to do a very strong check. That is to take our formula, make a particular specialization, and obtain a formula that was obtained by Ludwig some years ago. So let's start. The first layer in my discussion will be the web diagrams. I have to take you for a little detour because I will use many different concepts from many different areas. So we begin with the web. It is a very well-known fact that one can study 5-dimensional gauge theories. For me, compactified on a sphere is on an S1 is enough. And these theories, the low-energy theory of them can be captured by web diagrams in general that you can draw on a plane. For the particular ones that I care about, that they are supposed to capture the low-energy dynamics of the TN theories, here, they are here for you. They were written down by Benjamin and Chicava, and they were written down by checking some very simple symmetries and some very simple counting arguments. So these diagrams are going to encode the symmetries and the parameters that my theory has. So let's talk about the parameters. First of all, the formation of these web diagrams that do not change the asymptotics. They are equal to the number of faces of the diagram, and they correspond to the Coulomb branch parameters. And for this particular TN theory, they are n-1 divided by 2. And this is the Coulomb branch of the theory. The theories are 5D, and they are compactifying on an S1. These little A guys, they are going to be the 4-dimensional Coulomb branch parameter, and the A capitals are going to be the 5-dimensional, and beta is the radius of the S1. And then, the formations that change asymptotics, so of these external brains in the web, the number of the external parameters by -3 because we can shift the diagram, and there is also some conditions. So these parameters, they correspond, in general, they correspond to masses and coupling constants. Here I have no coupling constant because I said that fixed points. So I will have 3n minus n masses to describe the theory. Here in the picture, I depict for you the masses for the D3, and of course they obey a condition, you sum them to 0. So this is why I have 3n minus 3, and this is how I level my 5-dimensional parameter and my 4-dimensional parameter. Now, it is another very well-known fact that you can begin from these web diagrams and in fact calculate the partition functions using topological strings. This was one of the very important early success strings. So what you do, of course, you have to make appropriate identifications between the parameters of the topological strings and the parameters of the gauge theory, but you can explicitly show that the 5D Nekrasov partition function on an S1, they are equal to the topological string calculation that you are doing. And the way to do this is that you have to use what is called the topological vertex formalism, refined, okay. And you have 3 vertices. I give you the expression for the 3 vertices, expression for the lines, for the propagators. You write everything, you multiply everything down, and you sum over everything. Everything now is, instead of having momenta that we integrate, we have some representations, some partitions, over which we have to sum everything. Now, I just want to stress one more time, these theories that I want to study, they have no Lagrangian description, so this is the only way to go if you want to have partition functions. There is an extra piece of information that you have to add in order to be able to do the computation, and this is what we did, and by now it's checked and agreed by a lot of authors, that whenever you have a web diagram that has parallel external legs, that's not it, the old prescription. You have to actually subtract some extra degrees of freedom that are there. These extra degrees of freedom, they are, here I give an example, when you have only two parallel external lines, they are given by this special function and graphic that is given as this infinite product. Q is a parameter that will correspond to the distance between the two external lines, and little q frac and t frac, they correspond to the Nekrasov round. And one thing to notice maybe is interesting for this thing, and this is how you can think that you have to subtract them, is that they do not transform in a 5-dimensional representation. They transform as a 6 degrees of freedom. So they are really not of the same type what we want.
Is this the Heisenberg factor or not?
Let's not, I have a part to, let's and this is the expression. Now this is the full answer for what is the partition function of TM theories. Let's go slowly. First, I remind you that the answer is going to be on S4 plus S1. I have to divide by the extra degrees of freedom. And I will read off from that is this, the topological partition function. And then I have to do an integral over all the phases, over all the Coulomb moduli of the theory, in order to get the analog of Peston. And we do the integrals. So I have n minus 1, n minus 2 divided by 2 integrals in order to have a final answer. The topological string, here I write z perturbative z instanton. First of all, let me say, I don't mean that in this theory I have perturbative part and instanton part, there is no Lagrangian, no coupling constant. But this is a nice way to label things because they remind you of the structure that you have for Lagrangian theories. So the perturbative part, what I call perturbative part, is made out of this special function that I wrote before. And it looks very much like the usual theories that we have studied in the past. Of course, the detail is a little bit different. And then we have the instanton part, which is made out of another special function. This here is written here. Most of the people maybe that work only in 4D, they are used to the fact that this sign beta over 2 is not there. But this is the usual Nekrasov piece with which we write 4-dimensional negative partition 5-dimensional partition functions. Again, the detail of the structure is a little bit different, but it's what we are used to. And here, usually in theories with Lagrangian description, we have a coupling constants. Here there is no coupling constant, you have a combination of the mass parameters. So this is the formula, and I want to stress that this is not a beautiful formula. We still have another n minus 1 divided by 2 sums still left to perform. Now, okay, this is a very ugly formula, but you can look at it. Let's begin with t equal to with t n equal to 2. This theory, you can, in fact, you have no integral to do, very nice, and you have only one sum to do, and we can do it, and we can write the answer in this beautiful closed form. Immediately by looking, you can see that there is an SU4 symmetry, which is more than what you expected. You were expecting SU2 to the third. Let's do the same to do, but still we can expand. X is a combination of epsilon1 plus epsilon2 exponentiated. And we see that what we get, you can go as much as you want with the dots, organizes itself in a representation of E6. So we are here discovering that we have even more symmetry, more than SU3 to the third, we have E6. And the same thing has been done for T4 and T6. After, of course, the problem with this is that you have to specialize some of the parameters. And you discover that there is E7 and E8 symmetry. So the moral of the slide is that these partition functions, they have more symmetry than the naive SU to the third that we were expecting. Now let's turn to the CFT side, and to do that we have to use the AGT conjecture, which tells us that 4-dimensional n equal to 2 case theories of class S with SU2 or SUn factors, they are related to 2-dimensional Liouville toda depending on the SU2 or the SUn. And in fact the relation is very simple, it's exactly this. the Peston partition function, which is the square of Nekrasov, integrated, is equal to the correlation function on the particular surface with genus G and M puncture that we discussed in the first slide, where you insert the vertex operators of the UV or the total CFT. And the dictionary clearly goes that the instanton part corresponds to the conformal blocks of the 2D CFT. The perturbative part for UV, because for total we don't know, it corresponds to 3-point functions. And also there is the appropriate parameter identification that I guess most of the people know very well here. Now, let me review a little bit what we know for the 2D CFT. First of all, okay, we have the yellow book which tells us how to solve any rational CFT. The first evolution came by Dieuzy, who actually told us how to calculate, actually they wrote down, because they were very smart, the 3-point function of UV. And then Tessner came and he showed that this is indeed the answer by showing that this is a solution of a crossing equation. And now we go for n bigger than 2 for general total. And the 3-point function of 3 general parameters is actually not known. The state of the art for this topic, it can be found in Van of papers. Here I present you one of their formulas, which is take the 3-point function and specialize in a very particular way one of the insertions. You can write the answer in this compact form. This specialization corresponds to having a verbal module with a primary that has a non-vectoral level 1. So, now I come to discuss symmetries because this was the other important thing in the TN story. First of all, let me remind you, even in UV it's enough, if you have a vertex operator, you can think of it as in quantum mechanics an incoming wave with momentum A, bouncing off the exponential wall and coming back with momentum Q minus A. And for this is the reflected, this is the incoming, and we know how to calculate the reflection amplitude. This we know how to do it for UV, and also we know all the total generalizations with a little bit more group theory involved there. Now, Fatev-Lutvinov, in one of these 3 amazing papers, he told us that we can in fact split the 3-point structure constant into an invariant part under these Weyl reflections and a covariant part. Let's look at it for n equal to 2 for UV. The covariant part is basically the numerator of the previous formula that I showed you. And it's immediate to see that it takes all these 3 R's in it when it transforms. And the invariant part is basically the denominator up to a skew constant. And you can really take the formula that I wrote here and rewrite it in some nice variables that immediately you can see the SU form. So the UV, the invariant part, is symmetry than what you expected. The same thing can be shown for n equal to 3 for total. There is an E6, symmetry enhanced. So this, slowly, things are starting making sense. There is one more thing that I want to add, and then I will go to our proposal. The Q-deformed version of HB. And the Q-deformed version says that n equal to 1 gains theories on S4 cross S1. N equal to 1 in 5D is equivalent in 16 supercharges, equivalent to n equal to 2 in 4D, is related to Q-deformed CFT, and I guess everybody here is very used to Q-deformed CFT, so I don't have to say much more. Let me just say that my working definition is that basically you have to uplift your formulas somehow, very roughly, whenever you have an undeformed function. You write down its deformed counterpart. Here I have an example for the epsilon function that appeared in the previous slide. And I can also rewrite it in terms of this M-calligraphic, this other special function that I had when I was doing topological strings calculation. And all you have to check is that, first of all, when we take Q to 1, you get the formula that you have in the antiform theory. For the n-2 case, we know the 3-point functions. Nieri, Paschetti, and Passerini, they calculated it 1 or 2 years ago. And then we have to have, whenever we have a Q-deformed function, the same symmetries and the same zeros and poles, up to the fact that you have an infinite Q tower. You can think like a Kaluza-Klein tower. Now here is the proposal. This is the parameter identification that you have to do in order for the job to work. H's are some fundamental ways that, okay, this is some group theory way to project the correct components. And then you can show, first of all, that the y-covariant part should be mapped to this extra degrees of freedom. This is not a proposal, this is a calculation. This I'm not going to argue, this is correct if you do this identification. And then the Weyl invariant part should be mapped to the 5D partition function that I showed before in this exact way. Now, in these two formulas, there is one little thing that I have not said what it is, and I will immediately tell you now. What is that? Of course, we want to take the 4D limit. We want to study antiform total, the usual total. In order to do that, we have to take the limit for the circle to go to 0, beta to go to 0. But if you do this, this function that we calculated will blow up in your face. So the only way to do it is to multiply by a beta to some appropriate coefficient that is written here. And this thing, you don't even have to calculate it. Of course you can, but you can really understand it by using symmetries. And this is how. This guy is invariant under S U to the third. This guy is the same. So whatever I write here, it has to be invariant under S U to the third. So it can only be written in terms of Casimirs and nothing else. But then, I will show you in a moment, there is a formula, a Tevlut-Vinov formula, that is a specialized formula, and you can go and you can check that only quadratic Casimirs are allowed to appear in this formula. So then that's it. And then I have a complete proposal. Now, it is very important, and it would be very nice to have time to show you the detail, but I will not. You can do a direct calculation, take the proposed formula I showed you before, explicitly go and put in this Fatevlut-Vinov specialization, and the moment you do it, the integrals pinch and only very particular poles correspond, will give some non-zero answer. And then, the moment you calculate these very few poles, you can see that the sum sort, so the summand simplifies it, and you can actually do it. And then, from our proposal, it is possible, after doing this specialization, to show that we explicitly get the Fatevlut-Vinov result. And this is a very strong check of the proposal. Now, of course, you can do it with calculating, but let's do it without calculating. This is the 3-point partition function with 3 full punctures that I started with. And I know that I want to specialize to something that has U1 symmetry to one of the punctures. So I replace this young tableau by this. The moment I do this, I know very well from, of course, the work in the past, that this partition function corresponds to n by n free hypermultiplets. The answer for the free hypermultiplet for 4D was computed by these guys. The 5D partition function for a single hypermultiplet. And then you see, you take the Fatevlut-Vinov denominator, this is what I told you, that this is the invariant part, and you can just do the change of variables that I described, and you immediately can see that this is the partition function by hypermultiplets. Now, let me conclude. I gave you a formula for the partition function of these 5D Tn theories. This, through AGT, it led me to propose a formula for the 3-point functions of QD form total. Again, I want to stress, with all primaries generic. I also showed you that the 4D limit exists, and I told you exactly how to do it. I owe you to really write down the final formula. Okay, it's not written yet because you saw this beast is huge. You have to, care when you touch it. Then a very strong check that was we were able to specialize appropriately and get the fraternal formula. Something that in my mind is extremely important is that in both sides, in the gauge theory side and the CFT side, we have this symmetry enhancement. The gauge theory people and the topological string people are already caring a lot about this symmetry enhancement. We should also care of what is happening in the CFT, and we should really try to understand it. And I really believe, in fact, okay, I know how to do it, I think, that the moment you really demand that the partition function or the three-point function has this symmetry enhancement, you can immediately guess the answer in the closed form without having to do all these cubic integrals and sums. And then the last step to completely check and solve TODA and do everything is going to, we will have to start calculating what are the TODA descendants, and then we will start to glue them in order to obtain 4-point functions and then more. Yeah? So basically what I am proposing is that we can solve TODA using web diagrams.
Questions?
So what is the technical difference between about the 4D limit of the Gaussian partition function? I mean the difference between the one studied by Fraternal
Yes.
and the more general cases?
You have to do it with great care, because in the usual Nekrasov calculations, he immediately did it because he had the same number of n, you know, this Nekrasov piece in the numerator and the denominator, and all the diverging factors were immediately cancelling. In our formula, this is not immediate. You have to be very careful, and in fact, I showed you. This is the divergent part.
What makes it different? I mean,
It's just the structure of the formula.
okay.
You know, it is made out of the same stuff. That you have of them is just different.
Okay, but you somehow succeed in deriving the results by protecting the limit.
Yes.
But what if you want to generalize it? All 3-point functions. What is the main?
What
structure?
3-point functions do you have in mind? Because
Uh,
I don't know if I can. I mean, I only have a GT, and I can only do it for theories with, you know, SUM punctures.
okay.
So the
So in that one where you have a third.
can you be a little more loud, because I cannot hear? Sorry.
Sorry.
More loud.
Okay, so in that formula you are kind of specializing the parameter. Sorry, that formula.
Here, yes.
The parameter of the third guy.
Yes.
So if we want to have a more general thing,
So the more general thing, I wrote it for you. It is this formula. The moment you go and you put it here. This is the general formula. This is what I'm saying. I did.
okay, so is that a
A can be
form
anything.
Q-deform to that or?
The formula A can be anything.
Okay, so that's called Q-deform or?
This, okay, this slide was the outline and it was a little bit sketchy. If you write in front of everything limit Q going to 1, this is an exact formula.
Okay, yes.
This, okay, let me show you the exact formula. This is the formula with the Q's. And then you just have to put a limit in the front.
Oh, okay, that's it.
So in the in the case of Liouville field theory, there was an important check back in the day, which was taking the classical limit of the 3-point functions, and you could check it with the classical expectation you had from solving differential equations.
Okay, I
So
can
is
say
there
that this
a-
is work in progress.
Ah,
But to be honest, this is more powerful what we did.
the
This
afternnon
chamber
check.
is more powerful.
Okay.
The classical limit is very cool because this Nekrasov part splits into two things and it simplifies calculations a lot. So we have not finished it because we found a little bit that it's too easy maybe, but yes.
More questions?
You know everything that I know. What are you going to ask?
So 6 weeks ago, there was a paper by Gade, Willett, and Samat where they proposed some very, very strange
What they did is at the level of the superconformal limit.
I didn't finish my question because of the other thing. They wrote some very complicated Lagrangian for these theories. Kind of. They put it in the title in quotation marks.
Yes.
So, but you think it can be used for
Okay, look,
Lucas?
I didn't take the paper and start reading it and start calculating. There is some work. First of all, even before them, Tachikawa already proposed the Lagrangian distribution.
That was in 5 dimensions.
Yes. But 5 is better than 4, as we know very well in life. Yes, yes.
Questions? More questions? Then?
Perhaps having in mind the IGST application, supergravity, duals of that, is this formalism easy to take some larger limit?
Okay, I have to say something here. If this conference go on in the next 10 or 20 years, people will have to start taking n equal to 2 theories a little bit more seriously. And to be honest, I have been working on my whole life. It's very funny that I'm giving this talk here. So I want to say that there is almost nothing that is known for the n equal to 2 theories, we can really say we have IGST and everything. There is a lot of work to be done.
No, the question was technical.
Yes.
If you think that it's possible to take the larger limit or it's too complicated,
No,
things
you
like
can
that.
take the larger limit, but then, okay, I haven't done it.
That's
But
clear.
larger limit is always a good thing because simplifies it a lot.
Okay, I think we Okay, so our next speaker is Mariana, who will talk about the promotion science theory of the carcinoma.
Can you hear me? Okay. First of all, I would like to thank the organizer for giving me this opportunity to speak here. And today, and thank you for the introduction. And this is my talk, my title today. And if the keyword is not very familiar to you, then I put it here. So I would like to study N2 in M theory in terms of some determinant formula. So to explain my motivation, you need to know what M theory is. And for that reason, let me say that M theory is a magical 11-dimensional world. There live Alice and also two kinds of mysterious car soldiers, M2 and M5. And if you have N sheets of M2 brand, then this car soldier talk with each other with this kind of team count forms, and they need M to the 3 half team count forms. So you will see, if you see how mysterious this is compared with the usual situation where we need n squared T-count forms. So today I would like to explore more about this n to the 3 parts behavior. So this is the content of my talk. So first of all, I would like to introduce the ABGM matrix model, the matrix model to study the N2 branch. And after that, I would like to present our recent results here and tell you how beautiful this ABGM matrix model is. Then hopefully I have some time and I can tell you some generalizations. I start with ABGM matrix model. It was recently proposed by ABGM that N2 branch, when it put in this kind of simple orbifold, it is described by maximally superconformal n equal to 6 transaminase theory, where the gauge group is UN1 plus UN2. And the detail is K and minus K. And besides vector multiplet in adjoint representation, we also have hypermode multiplet in the bifundamental representation. And if N1 and N2 are equal, we only have N2 branch. But if one of them is bigger, then this will be some fractional N2 branch. So let us define the S1 bracket to be partition function or vacuum expectation value of half BTS Poisson loop in representation Y in this theory. Then originally this vacuum expectation value is expressed in infinite dimensional class integral. By using the localization techniques, we can reduce it into finite dimension, just a numerical factor. Then it is a multiple integration over quantity Sy with N1 plus variables. And when we do the integration, we need this factor. Here N1 and N2 are the ranks of gauge group, so should be integer. And K is the level of the theory and should also be integer physically, but for most cases we take it to be a real number. If you are familiar with localization theory, let me tell you that the one loop determinant of vector multiplet, this gives you the numerator, and one loop determinant of the hypermultiplet, this gives you the denominator. And here Sy comes originally from half BTS Poisson loop operator, and it is classified by Young diagram. And more technically, so this guy is just so it's almost a Gaussian integration, but since you have imaginary unit, it's called a Fresnel integral. And this Sy is the character of supergroup UN1/N2 in representation Y, and it is usually called supersymmetric Schur polynomial. And for this part, it's basically the Fundel measure, but it has two kinds of deformation, Q deformation and Suzy deformation. More explicitly, we start with the Fundel measure, which is UN1 invariant measure. And on one hand, you can do the Q deformation by replacing the rational function in terms of trigonometric function. And on the other hand, you the UN1 invariant measure by supergroup UN1/N2 invariant measure. And if you do these two kinds of deformations simultaneously, then you obtain this measure. So the ABGM matrix model has this kind of simple explanation. So my message here I would like to stress is that ABGM matrix model is as fundamental as the most standard Gaussian model or Chern-Simons matrix models. So this is the ABGM matrix model. Then I would like to tell you two results from our study. ABJ case where two ranks N1 and N2 are equal with each other, and I denote it like this. And Jump-Ready identity is among half BPS with a loop. And this example expansion is some explicit formula written in terms of topological string. And if you want to generalize the story to ABJ case, and we can generalize, but here for simplicity, let us not consider it here. So let me start with the Jump-Ready identity. The Jump-Ready identity is a classical mathematical formula stating that the supersure polynomial of this kind is written in terms of determinant of some other supersure polynomial. And here sy, as I told you before, is a supersure polynomial, and it is character of un/n in representation of y. And here for y, for the Young diagram, I use Frobenius symbol, and I depict it like this. So pictorially, the Frobenius symbol is defined as follows. It is defined by counting the numbers of the boxes from the diagonal line. So here you find 6, 5, 3, 0. So you write 6, 5, 3, 0 here, and here you have 6, 4, 2, 1. So the Jump-Ready identity tells you that the shear polynomial of a general Young diagram can be written as a determinant of the shear polynomial in the hook diagram constructed by all the combination of arms lengths and leg lengths. And this is the shear identity. So far, it is a classical formula for the loop operator. So the next thing, the next question you want to ask is whether it holds quantum mechanically. So for this purpose, let us define the ground canonical ensemble, the vacuum expectation in ground canonical ensemble. Namely, you start with the vacuum expectation value before, and you introduce the fugacity g and define a generating function here. And then you normalize it in terms of ground canonical partition function to be this ground canonical bracket. Then you can prove that this Jump-Ready identity originally for the supersure polynomial is actually correct after we introduce this kind of ground canonical bracket. So pictorially, Jump-Ready identity is this one, and it calls for Young this shear polynomial, but we can put the bracket in the sense of vacuum expectation value in ground canonical ensemble here. This is the first. In a textbook, it usually tells us that when we have a symmetry, then it will lead to the Ward-Takahashi identity. But here we find that there's an identity classically holds, and it still be correct. And after we do the Cauchy integral. So, but this is only true for the non-canonical vacuum expectation value. And this might imply there's some hidden symmetry in this system. This is the our first result. And so this Jump-Ready identity is very beautiful, we believe, but it is rather kinematical. It doesn't refer to the explicit form of this bracket. So the next thing I would like to tell you is a more dynamical one. Namely, we consider this expectation value explicitly. This the partition function, the study of partition function was initiated by this n to the 3-power log, and it was found that the log of this function is written like this in the large n limits. And we find that this expression, of course, has all kind of perturbative corrections, but we find that this perturbative correction can all sum up beautifully into an airy function. Recently, this result was generalized by Lim Yao Zhou, and they found that this kind of airy function behavior is very universal and holds for most theory. The physical meaning of this airy function can be understood as follows. So we can define as before, we can define the ground potential out of the out of the partition function by introducing the chemical potential mu. Then we can compare the inverse transformation with the integral representation of airy function. Then we find actually they are very similar. And so this kind of similarity tells us that instead of partition function itself, when we since this cubic function is much simpler than airy function, so instead of the partition function itself, when you want to see the large n expansion, it is much easier to see it from the ground potential. In fact, this kind of transformation has an interpretation of seeing the free energy of topological string theory from a different point in the moduli space. And this mu to the cubic function represents the Yukawa coupling. So in this sense, the previous result by the previous generalization Yao is very natural. We can go beyond to study non-perturbative part, and we can find that the non-perturbative is written in terms of various limits of the free energy of refined topological strings. And this is so you might wonder how it was found and whole cancellation mechanism, which I don't have the time to explain. But this is how this explicit expression for the partition function was found. So far so good. So we have solved the ABGM matrix model, but we can ask why this model was solved and how it was solved. And so for the perturbative part, it basically comes from the Fermi-Gas formalism. And for non-perturbative parts, we don't know. There are lots of reasons it was solved. The maximum Szilzi integral model relation to topological system. And for the geometry identity, probably the supergroup plays an important role. So if we want to see the generalization, the first step is to see whether the Fermi-Gas is applicable in your generalization. So the generalization we want to consider the generalization next. So this is a generalization we want to consider. So we regard the ABGM as the simplest circular quiver. Then we can ask how about the general circular quiver? How can we apply the Fermi-Gas formalism? Or we can regard the circular quiver as the thinking diagram of affine A type. And then we can ask how about the affine B type or affine P type. Here for this kind of thinking diagram, there's if this kind of thinking diagram can be characterized by the property down the number, so that twice of the number is the sum of the adjacent vertex. For example, twice of 2 is 4, but here when you sum up 1, 1, and 2, then it becomes 4. And this holds for all the vertex. But this kind of and this number are called comax. This kind of property can be characterized from the physical viewpoint. Namely, we start with n equals to 3 theory, and it can be defined for a general gauge group and methods. But we can refine we can require a balance condition so that the long-range force has to be vanished. Then balance condition gives us this condition to force us to consider the ADE classification. Then for balance quiver, if we want the conformal condition, then we have to further require this condition for the level K. So today I would like to tell you the Fermi-Gas formalism for variance quiver. After reviewing the previous results by Marino Putov on affine A-type quiver, then I will go to tell you how the Fermi-Gas formalism is applicable to the affine E-type quiver. So this is our setup. We have all the factors everywhere with different levels. Conformal condition tell you that the sum of level has to be 0. Then at the Abelian case, the partition function is written as an integration, multiple integration of this factor over this factor. Here the numerator comes from vector multiplet and the denominator comes from hyper multiplet. So and here everything is defined as before. And so let us concentrate on this major part first. And this major part is in the denominator, in the numerator it's square, and in the denominator it's just single power. So we can split the vertex into two parts and rewrite everything like this. Then using the Cauchy determinant, give you this formula, we can rewrite it as a product of determinants. Then we plug this measure back to original expression of the partition function. And then there are a lot of integration of the product of determinants. But we can use this determinant product formula to combine these determinants one after another. We combine everything, then finally it becomes a single integration over a single determinant. Then this is the result. And if we define this part to be a density matrix and you expand the determinant, you find that this is the partition function is given by the density matrix propagating from one coordinate to the permutated coordinate with a certain sign factor coming from determinant. This is nothing but the Fermi-Gas expression. We can further rewrite the density matrix in terms of Hamiltonian. Then the Hamiltonian is given like this. And if you do the similarity transformation, then this U becomes this S is defined from this relation. This is the relation for a hard quiver. So next, so this Fermi-Gas formalism for the affine A quiver guarantee you that. But except the leading order behavior, most that are unknown. So this is a story for A-type quiver. So next, let us turn to quiver, which we did, and also Axel Drucker Felix did recently. And for the D-type quiver, the thinking diagram is 1, 1, 2, 2, 2, 1, 1. So if we label this vertex by mu and mu prime, then the level has to satisfy this relation, and so we can parameterize each expression by this case. So again, we pick up the major parts. And for this case, for the D-type case, we can multiply S and divide by S, and then this square S is defined like this. Then we find that each factor is actually rewritten in terms of determinant again. So everything is again indeterminate. But the different thing is that here, so we can use the determinant product formula to combine this determinant in the middle as L, and using two endpoint M and N, then we can do the same multiplication and rewrite the partition function into this form. And after you do another integration, then you will find that actually instead of determinant, Papillon has appeared. And this Papillon is the unoriented, has an unoriented structure. So this gives you that when you rewrite everything in terms of Fermi-Gas formalism, it is you have to come from here, but you have two ways to go, this way or this way to go. And this will give you the Fermi-Gas formalism for the D-type quiver. So again, for both affine A and D-type quiver, as long as Hamiltonian is Hermitian, we find the Airy function and behavior for C unknown. And but this is just for perturbative. If we want to study the non-perturbative effects, we have to some hints from the supersymmetry. And Imamura and Kimura shows that when this S is only plus minus, it only takes plus or minus 1, the supersymmetry is enhanced to n equal to 4. And especially when plus 1 and minus 1 are separated, for the level we have lots of 0, and this tells you that there are no dynamics in this part. So in this sense, the dynamics is minimum, so we call it the QP model.
What is the state?
I'm sorry? What is
SA?
SA is the one I show you previously, this one. So we level K, so the sum of level K has to be 0, so we level it as SA. Thank you. So the situation is that we have the most symmetric case, and we understand ABGM theory. But for the most general case, n equal to 3, we still don't know. So we want to study the middle one by supersymmetry. So I want to tell you unfortunately I run out of my time. But fortunately my young collaborator Nosaka is giving a poster today, so he can tell you more detail. And let me just note that despite all the progress, only these 4 theories are solved. So recently there are lots of papers, but only these 4 theories are solved. So we want to solve more theory instead of instead of just pick up some point in the moduli space, we want to solve the whole theory to understand the universal structure of the M2 brane. Also, we have done the affine D-type quiver, but E-type quiver is missing. And there are 2 steps, as I told you. We put it into determinant and we express it Q and P. But they are most of difficult, and for this part even desperate. But fortunately, the leading behavior was already given in this paper. So we believe we can pursue this project. And hopefully, in the step 2, besides Q and P, maybe we need some more operator, but still, this should be some handleable operator. Sorry for being there. Thank you.
Questions?
Oh, in the very beginning, when you considered pure of a BGM case, you had expression involving supersymmetric determinants, van der Waals, and supersymmetric Schur polynomial.
Okay.
But it's a supersymmetry for n1/n2. And in original BGM, I think there is no hint of such supersymmetry. I mean, why it has a supersymmetry? For instance, when you go to high quivers, then obviously
You are talking about, sorry, you are talking about this story?
No, I mean, your expression has supersymmetry should polynomial, but the supersymmetry is for SUL1 / N2. There is no such supersymmetry in origin.
Oh, okay. You're saying, so yeah, and in fact, I'm confused the word super in two senses. And the first one is supersymmetry in the field theory, and you have a supersymmetry to transform every field. And the other super is in the sense of supergroup. And originally they don't have any relation, but for some reason it come out.
Yes, the question: do you have any idea why? And what is the analog of this generalized when you have high field?
I think this is some coincidence because for example, super Yang theory you have supersymmetry, but still you typically don't encounter any super algebra, super gauge symmetry. But so this is coincidence in some sense, only happens in ABJ and case. But I think it's not just the not just this case. Even you put the orientable to make it into OSP something, it still has a supersymmetry. So I don't know why, but this is what people found.
More questions? Okay, so now we have post session for half an hour, so we will be back here 5 minutes.
We come back at 4:15, 45 minutes.
Yeah, we might have got text. Set that coordinate, which is like a null coordinate, equal to the worldsheet tile.
depends. I mean, of course, it's always good to get impact. It's always good for tomorrow. Things that would be good to develop. So you can do a PhD from which university?
Will be Waterloo.
Do you get a Joseph permit or is it not the same way it's Waterloo?
So
In Canada, it's always Waterloo?
it's always Waterloo.
Or you
Maybe
can
it's
go
also
direct?
Guelph. There's a few universities. I think it just depends on where your advisor is officially.
Your official advisor is pretty
Actually, no, I think Rob Myers might be officially my maybe okay. No, he's at least co-supervisor. There's something there. I needed at least someone who's.
polar opposite, yes. He is. But come on, he does quantum cohomology. You can't hope for anything different.
He could be, you know, slightly overweight, gregarious personality, which he is.
He's not. He's very special in many regards. So how's the streaming going?
I think Korea is perfect for him.
Yeah, that's what I told him.
Korean movies are just
That's what I told him that. Yeah.
amazing.
Who writes it?
Cultural Institute.
That sounds like him.
And then he was going to St. Pancras to play the piano with him.
Yes. I know. But he's a fun guy. I don't know. I don't want to know. Oh yes, pentacork. Did you hear that it seems that LHCb observed pentaquarks?
Did they observe pentaquarks?
They observed the resonance in the J side that could be whatever compatible with pentaquarks, and you know we were all waiting for stops and diquarks, but no one pentaquarks. Actually, can I show you one wonderful quote I found? I don't know if you know this.
This is pretty late now.
No, he said a quarter past.
A quarter past. Oh, I missed that.
I missed that too, but I was told here that. Do you know this guy Rhodes that wrote this book about the making of the atom bomb?
Do I know that guy? Maybe I don't.
Lorenzo told me about him. And
Lorenzo.
yeah.
But my God, you guys are like high school friends.
No, we spent 1 week bullshitting together.
I haven't spent 1 week bullshitting together with David.
Yeah, but I mean, come on. I mean, nice guy, absolutely, but you know.
Audio Libri.
I have no idea.
You have Audio Libri?
No, but here's every guy is there.
The problem is you can't search.
No, I can't. That's just what the fuck. By the way, I started reading in some masochist outbreak the Ruel Statistical Mechanics Rigorous Results. Jesus fucking Christ.
Why did you do that?
I don't know. I have no idea. I mean, it's masochism. This is the book. This. Show this quote by Segre.
Yeah, I think I knew this.
Didn't know. It's quite good.
And actually, this cross you can't guess that. No, it's impossible. You just have to be measured. And some of them I think were very surprising. So I have Sage tools upstairs in my office.
You have? Really?
Yeah, just go to searchmycloud.com and make yourself an account.
Sage?
Cloud.
Are you fucking killing me? Sage my cloud. Math cloud? Okay. Okay, that's cool. Just need on my one iPad. If this bitch loads. go on holiday? I don't know. It could be, but yeah, no, I guess they're not really stringing up. Well, that actually comes to something. Yeah. Have you seen Gerard? I'm sorry? Have you seen Gerard? Yeah, he gave us a seminar about Gerard. Yeah, he gave us. Well, you know that yeah. Probably back okay. Yes. This is I guess supposed to be. Where do I log out? Oh, which one? Okay, W algebra. Yeah, okay. Is it I something or okay, never mind. No, I guess the time was for a while. No, I spoke to IGST. What's up in Durham? Okay, well, we just had this incident. Yeah. No, that's not yeah, is any other going to be online? Ultimately, yeah, I've got 60 gigabytes of my laptop. But on video? Yeah. It's actually I'm hoping that the people at the day right. You should really put it on YouTube. It's not the easiest thing. Have you been asking speakers here whether they mind being online?
There is a form.
Right.
I don't know how we can find it yet.
Yeah, so in Durham, I think I asked one or two of them. I think somebody said it was as long as it's just on. But they were so well.
Okay. So the last speaker today is John Canada.
The format that's easiest.
Okay, so today I'll talk about computer school Wilson loops and support using integrability. Now, Wilson loops are a natural variable to discuss the gauge gravity duality or gauge string duality because Wilson loops have a very natural interpretation on both sides of the correspondence. And the correspondence between n equals 4 and type 2b strings in ADS process provides really a perfect example of this. And there the dictionary tells us that to compute some Wilson loop associated with contour C, we should sum over all, we should compute the string partition function as a sum over all surfaces in ADS which end on the same contour C, sitting at the boundary of ADS. Now, in the case of n equals 4, the string tension is proportional to the Tooth coupling. So, in the limit of large Tooth coupling, this sum will just the classical term for the minimal area, and the problem of computing this Wilson loop just becomes out of computing minimal surfaces in ADS. And this is really the parameter regime I'm going to be concentrating on today. I'm going to be talking about the strong coupling limit of n equals 4, and therefore I'll just be talking about this minimal surface computation. But I want to emphasize from the start that if you're really just interested in computing minimal surfaces, you might as well just solve the string equations of motion in ADS numerically and compute the area that way. The point of really having an integrability-based formulation of this problem is that, at least based on examples, what we've learned is that integrability really provides the natural language for generalizing to finite coupling. And examples of that are the success of the spectrum problem and also this ODE pentagon program, where in both cases the idea is to develop an integrability-based formulation in coupling and in strong coupling, and then that gives you a natural language to generalize to finite coupling. So in the last several years, there's been huge progress in computing minimal surfaces in ADS, and in particular in the case of surfaces that end on these light-like contours, or so-called null polygons. Some beautiful technology has been developed for computing the minimal area associated with these types of surfaces. And this was done by these authors, which I'll refer to throughout the talk as AMSP. Now, what was done in this beautiful paper of AMSP is they understand for the first time how to utilize the integrability of the string equations of motion in ADS in order to compute the minimal area of this surface. And their solution gives you a general prescription for any number of cusps in any configuration. Okay, so someone interested in computing smooth Wilson loops or minimal surfaces ending on smooth contours would naturally have the idea that, well, I can just take the result, I should take the limit of a large number of cusps, and in that way I can obtain equations that should compute for me minimal areas ending on smooth boundary contours. And that's what I want to say, but I should say from the beginning that it's not just a matter of taking the formula of AMSB and taking n to be large. It turns out to be somewhat of a subtle problem, and that's part of what I'm going to address. So the starting point of this AMSB construction is to first take the ADS3 sigma model and to reduce to a set of R22 invariant, manifestly R22 invariant coordinates. This is just the so-called Holmeyer reduction. It was mentioned yesterday by Ben. And in this construction, the positions of the cusps or the shape of the boundary curve get encoded into a holomorphic polynomial P. So this polynomial is constructed from some R22 invariant combination of the embedding coordinates. So this Z here is really the world sheet Z. And it's just a holomorphic polynomial in Z. So, and well, more precisely, I should mention that, of course, the actual area of the surface is divergent due to the cusp. There's some cusp divergences. And once you regulate the area of the surface by removing these cusp divergences, you're left with a finite conformal invariant area, which depends only on the cross ratios of the positions of these cusps. And the precise statement is that these cross ratios are into these cycle intervals of this polynomial P. Okay. So we can do a bit of counting. So for a null polygon with two n sides, the degree of the polynomial will be n minus 2. Okay. And such a polynomial has n minus 3 independent cycles, which gives you exactly the 2n minus 6 that you need to parameterize these cross ratios. So actually, I should have said in the very beginning that throughout this talk, I'm going to concentrate on the case of ADS3. Okay, so this corresponds to a Wilson loop that can be embedded in an R11 subspace of the full R13. So its strong coupling just becomes to a minimal surface which can be embedded in an ADS3 subspace of the full ADS5. So that's why we have 2n minus 6 cross ratios for a polygon with 2n sides. Okay, so let me just explain then how this AMSB solution works. That once you've computed these cycles, the solution is just constructed as basically this TBA system. So the cycles enter here and also here. These phi's are just basically the phase of these cycles. And so you plug the cycles here. This intersection matrix here just gives you the area. Okay. So then to reconstruct the geometry of the actual curve, it comes from evaluating these y functions at special values of the spectral parameters, 0 and pi. It gives you back the values of the cross ratios in the physical terms. So I've been quite schematic here. In particular, there's of course an enormous number of different cycles you can choose. By the way, I should explain this picture. In this picture, this is just a picture of the polynomial P of Z. So these little yellow x's are really the zeros of P. This is the Z-plane. This is an example of a cycle. So of course, there's many possible cycles you can choose, and I haven't specified it here because exactly what cycles appear in this equation depend on how these zeros are configured. And that's sort of the key point in taking this continuum limit is the fact that as you start moving these zeros around, these equations always maintain this schematic form, but they change in the cycles present here change depending on the positions of the zeros. Okay, you can think of this as this change occurs because of the need to analytically continue these equations, but the basic point is they always maintain this form up to the fact that you can have different types of cycles. Okay, so what we need to understand now is how to take the continuum limit in terms of this polynomial P of Z. So of course, we need to take the number of sides to be large, so we need to take the degree of the polynomial infinity, so we're going to have a large number of zeros. An infinite number of zeros, but we need to understand how to arrange those zeros in order to obtain a smooth boundary curves. Okay, so in order to have cusps accumulating in a way that they approach smooth curves.
Can you say more? So the lines of polygon transform to zeros with P of this.
So the map is a bit complicated. Okay, and
so is it easy to go to zeros with P from the polygon or directly A and B?
No, the map is much more implicit than that. And let me return to your question at the end, okay, because it's an important question. So for now, just think of this as a very convenient Yeah, so let me say directly that these Z's can be eliminated in terms of the cross ratios themselves. So you can write these equations directly in terms of the cross ratios. But you lose analytic control of the asymptotics, which will be quite convenient. So for what I'm going to do, so you can think of this as just a very convenient parameterization for the analytic continuation, which is necessary for taking the continuum. But that's making it more precise. Okay. So basically, what drives the solution to the boundary is the divergence in P. So in the case of the null polygon, this polynomial goes to infinity as z goes to infinity. So this boundary, it's infinity in the z plane that maps to this boundary. Okay, so what we want to do if we want to generate a smooth boundary curve is we need to generate a contour in the z plane where this polynomial jumps rapidly from finite values to infinite values. Okay? So let me explain how to do that. So consider 0, 0. I have two groups of zeros. These yellow ones can just be scattered anywhere, and these red zeros I've put precisely on the unit circle. Okay, so this corresponds to a polynomial like this. This piece contributes to the red zeros. This is the yellow zeros. And I want to take the limit where n goes to infinity. Okay, so in this limit, outside of the unit circle, this c to the n will become infinite. So the polynomial will limit to infinity. Okay? Inside this unit circle, this 3 factor just becomes -1, and what's left is just this residual polynomial, which is just the product over these yellow zeros. So this is exactly the situation we want. We've created this scenario where the polynomial jumps rapidly from some finite values to some infinite values along the unit circle of some kind. Okay, so in the actual target space, when you use the embedding coordinates to map back, is this red contour is going to map onto this smooth boundary contour, and this gray disk is mapping into the interior. It maps to the world sheet in the bulk of ADS. Okay? And what's parameterizing the shape of the boundary curve now is these residual yellow zeros, which give you this residual polynomial here. Yeah. Let's go to some configuration like this, which is studied by ASV and written in their paper, correspond to the case where all of these zeros are arranged along the real axis. And one way we can, so for now, forget these yellow zeros, let's just worry about the red part to generate the boundary curve. So one way we can work out how to the TVA equations for this configuration is just to analytically continue these equations by moving the zeros into this configuration. And when you do that, what you find is that this is, so by the way, I should explain the meaning of this picture. So these blue lines represent the cycles, these z's, which are present in this TVA equation. So when the zeros are arranged on the real axis, these are the cycles that are present. You really just have this nearest neighbor connectivity. So if you number the zeros, 1, 2, 3, etc., you have a cycle z12, z23, so on and so forth. And again, this intersection matrix is really just the intersection matrix of these cycles. So if two of these blue lines both touch the same zero, this intersection matrix is 1, otherwise it's 0. Okay. So this picture really just encodes these equations. And when we analytically continue into this configuration where the zeros form a circle, or they're configured on the unit circle, this is the TVA we found. So again, it's given by this, but now we have all of these cycles present. Okay? And in general, for any number of zeros, when you go to this configuration, what you find is precisely this, that the cycles present form this complete graph.
Sorry, but that's much more than
That's right. So what I told you is that when you start analytically continuing, new cycles can appear. So it doesn't mean that you're adding cusps to the polygon, because you always have the same number of independent cycles. The new cycles aren't independent. These cycles actually form a basis of the possible cycles. Okay? But as you start to analytically continue, what happens is pulls of the kernel across the contour, and you need to add, basically, you need geometrical models that's really like forming a bound state. So you need to add some y function to describe the dynamics of that bound state. Okay. So this is what we find. And again, the general, for any number of zeros, the general rule is that the cycles form this complete graph. Now that we have, I should say that, of course, I've only talked about forming this boundary here, but of course we also want to add these residual yellow zeros to generalize the solution. So I've added them here, but I haven't drawn the corresponding cycles. And the reason for this is that when you add these zeros outside of the unit circle, in the limit where you take an infinite number of when these red zeros, number of red zeros go to infinity, of course, outside the unit circle, the polynomial is becoming infinite, and so these cycle integrals are becoming infinite. And what it means in the TBA is that this source term is becoming infinite, and that y function is just decoupled. So I don't need to add the blue lines for the y functions corresponding to the external zeros. But I should say that by adding these zeros, you do affect the values of the integrals inside. Okay? Because, of course, this is what the interior limits to this function, which is the product over these polynomial form product over these zeros. Okay, so now that we've identified the correct form of the TBA for the continuum limit, it's really just a matter of plugging in the scaling of the y functions with n. Okay, and really, when you plug that in here, you really get directly the continuum. But it's a nice opportunity to show really how important this analytic continuation was. So if you study the scaling of the y functions with n in this region, in this MST region, what you find is that they scale like n squared. Okay, and you have order n y functions. So if you plug this in, what you find is that you don't get any sort of sensible continuum limit, right? Here are n terms where the y functions are scaling like n squared. Basically, nothing, you get no nice continuum behavior out of this, right? The equations don't describe any sort of continuum limit. Okay? Whereas in this region, you get really the perfect combination. You find that the y function scale is 1 over n squared, and moreover, you have n squared up. Okay, so now you're summing over n squared terms, and each term is proportional to 1 over n squared, which is precisely what you need to get to turn the sum into an integral. Okay, so that's really exactly what I'll do. Now I just take the limit where I take an infinite number of these red zeros to go back this way, and I plug this scaling into the TBA. So the y function goes like 1 over n squared times a finite piece, which still depends on the theta. Okay, and literally plugging this into here really gives you the continuum equation. So the left-hand side is self-explanatory. This epsilon is 1 over n. I've really just plugged in. On the right-hand side, what happens is you expand the log. Okay, this gives you a 1 over n squared, which you combine with the intersection matrix. Okay, and this exactly turns out to be this integral, which, so let me explain that. So of course, you expand the log, and this gives you this y function here, and provides a 1 over n squared to turn this sum into an integral. So the limits of integration here come precisely from this intersection matrix. So I should actually mention the additional rule that when two of these blue cycles cross, the rule for the intersection matrix is that it's equal to 2. That explains the cancellation of this 2 here, actually. But, okay, so the rule is that we're summing over all, so let's say we want the TBA equation for sigma 1, sigma 2. We should sum over all y functions such that these two blue lines cross, okay, which means we need to sum tau 1 from sigma 1 to sigma 2. That's this integral here. And we need to sum tau 2 from sigma 2 to sigma 1, which is this integral. And the divergence in epsilon comes from the fact that when there's actually a short distance singularity in these y functions when sigma 1 and sigma 2 approach. Okay, so in the integration region, this comes from when tau 1 and tau 2 both pinch down on sigma 2 or on sigma 1. Okay. But this is actually quite easy to account for. You know actually analytically the form of that singularity, and so you can easily just subtract it off. So this y circuit is just really some simple analytic function with the same short distance singularity that I've subtracted. It doesn't depend on theta, so you can just add and subtract and then integrate out. And the only effect on the equations is to cancel out the epsilons and to insert this y circuit on the right side. Okay, so this is really the continuum form of the TBA equations. This is the continuum generalization of the null polygon equations. I won't derive for you how to take the continuum limit of the area because it actually turns out to be a very, more or less, the most simple guess based on what we learned from the TBA. It's sort of the simplest generalization of the discrete area. So basically, you just, in the discrete area, you replace this sum over s's with these integrals over sigma. This comes from expanding the log. You get again a 1 over n squared, and it's just nicely inverse to an integral. It's over all values of sigma 1 and sigma 2 because you don't have an intersection matrix. So the only thing in this equation that you don't really expect is this appearance of this minus 2 pi and this y king. And this just comes from the fact that the regularization in the continuous case is very different from the regularization in the case of the null polygon. Where in the null polygon you have cost divergences, whereas in the smooth case you have an arc length divergence. Okay? So the way we're regulating the arc length convergence in this area formula is basically to subtract off a circular Wilson loop with an arc with the exact same arc length. Okay? So that's what this subtraction of yt does. You're really subtracting off the area ending on the same arc length, so you cancel the arc length convergence, but you need to add back a finite piece of the circular solution. So that all you're canceling here is the divergence. And that's where the area formula comes from. Again, to reconstruct the final boundary curve, it's just like in the IGST equations. You evaluate these y functions at some special values, and you recover the cross ratios, which are now continuous. This continuous curve has a continuous set of cross ratios. Okay. That I want to note, of course, this whole derivation has been manifestly Minkowskian from Minkowskian boundary, because I'm talking about null polygons, but there's actually a very simple adjustment of these equations such that they're valid for Euclidean ADs. And basically, all you need to do to adapt the equations to Euclidean ADS is to insert the space factor in front of the source and to change in the area. And basically, well, the way to obtain these is, I mean, this is basically the simplest guess for the equations based on the difference between the Minkowskian and the Euclidean flat connection. But then you can check actually that this is the correct generalization or the correct deformation because you have many exact solutions in the Minkowskian case. Sorry, to check it.
How do you see the 1/4?
The I before.
I mean, yeah, why 1/4?
So basically, if you look at, so where this guess comes from is really taking some exact solutions from the Euclidean case and looking at their asymptotics. Okay, so this term controls the asymptotics. What you see is that generally in these y functions, in the asymptotics you have lines and poles. Okay, so in the Minkowskian, poles are directly opposite from each other as you go to theta minus infinity to theta plus. In the Euclidean case, you find that they're offset by exactly I over 4, which is where this shift comes from. Don't know if you're asking for a physical reason, but okay, physical reason I can't tell you, but mathematics will study asymptotics. Okay. One more thing I want to mention is that, so as I've said before, in the continuum you can think of the shape of the physical boundary curve being parameterized by this residual polynomial p, okay, which is the sum over these yellow zeros. But you can alternatively, another way of thinking about it is to perform this conformal transformation here to this coordinate w, which basically is the conformal transformation that sets this polynomial to 1 at the expense of deforming the boundary contour. Okay, so this is just this red contour maps to this red contour under this change of variables w. And in this parameterization, you can really think of this curve w of sigma as parameterizing the continuous boundary. So it's a matter of taste. It's also nice because this parameterization sort of makes contact with known solutions in the Euclidean case. How am I doing for time? Have fun. Okay. So an interesting thing about the continuum, these continuum equations, is that they actually admit exact solutions in some special cases. And this is really somewhat surprising because in the case of the TBA for the null polygons, for example, there's really no case where the actual TBA equations themselves can be solved. There is the case of the regular polygon where you can compute the area analytically, but you still can't ever solve the TBA themselves for the y functions. Of course, if you can find the area, I'm not sure you can. But a surprising thing about the continuum cases, there's really situations where you can not only compute the area exactly, but you can really find the exact y functions. So the canonical example of that is when you choose this curve W sigma to just be a circle of some radius r. Okay, so this r is a parameter of this solution. And in that case, you can write an exact solution, so you can write the y function exactly in terms of some so-called functions, which are like an elliptic generalization of Bessel functions. And the exact area in the boundary curve can be computed also in terms of these Matthew functions. So I won't write the actual expression. Actually, I'll write the expression for the area in a minute, but I won't write the expression for the y functions because, well, the cutest thing is just that the solution exists. I'm not sure the actual form of the solution. So let me explain what this looks, the physical solution in the Minkowskian case. So when this worldsheet curve, when this r goes to 0, so this circle squishes down to a point, the physical solution approaches that of the circle. Okay, so in the Poincare patch, it's this straight line. In the cylinder, it approaches this surface. On the other hand, when you send this r to infinity and you blow this curve out to cover so that this red region covers the whole W plane, the solution approaches this the null square. Okay, so in the Poincare patch, it looks like this, and in the coordinates, it looks like this. And for intermediate values of r, it's some funny solution which interpolates between these two. So here I've drawn what it looks like. Okay, so it's this funny solution which interpolates between the circular solution and the null square. So, but I should make the important comment that for any curve W of sigma, so for a curve of any shape, when you collapse it to a point, the solution will approach the circle, and when you blow it to infinity, it will approach the null square. So this exact solution is just demonstrating in a specific example that interesting fact that any curve contains these two limits. Okay, so in the Euclidean case, as r goes to 0, of course, the boundary curve, so in the Euclidean case, the boundary is really locally r2. So when this circle is small, on the boundary you have really a circle. Then as you start to increase the radius of this W curve, the solution on the boundary starts to deform. It gets to this point, this is around r equals 1, and then it starts to do this funny thing of twisting around, and in the limit of r goes to infinity, it forms these two spirals. Okay. So the exact area can be computed again from these matching functions. It's given by this. This A of r is just this so-called matching characteristic. And I've plotted here what the area looks like as a function of r for the Euclidean case. So you can see that as r goes to 0, it approaches minus 2 pi. And as r increases, it goes down to minus infinity. It's interesting to note that the first deviation at small r actually matches the prediction from way to 1. Okay. So with that, I'll finish and just comment on some future directions. And I'd like to go back to what I said at the very beginning, which is to say that the ultimate goal is really, of course, not to compute the most general minimal surface. The ultimate goal is to compute Wilson loops at finite time. And for this, maybe we can take some inspiration from this OPE pentagon program. So let me remind you that in this OPE program, the idea is to write the solution as an expansion around the null square. So you separate the null polygon into a top and a bottom, and you identify, you can really see that the solution takes the form of the sum of the particles flowing from the top and the bottom. And in the strong coupling that problem, you really still see that same sum. So when you expand the strong coupling TBA in the null polygon problem, you really still see this sum over particles flowing from the top to the bottom. One particle, two particles. So one thing we could try is to do the same expansion with this continuous TBA, to try to expand this TBA. So again, as I mentioned before, this limit when you blow the W sigma out to infinity really corresponds to the four-cusp solution. So one could imagine expanding around that limit and trying to identify the terms as a one-particle term, a two-particle term, etc. And this should really give you a good idea of how to generalize to finite. And so, of course, well, with that lofty goal aside, there's still plenty of concrete work to be done at strong coupling itself. One is really to work out the full ADS5 equations. So again, everything but let me mention that the starting point, these AMSB equations, the ADS5 generalization is of course known, and one could really try to repeat the exact same procedure of that I've described here of identifying how one should deform the polynomial to affect the continuum limit, to find the form of the TBA for that polynomial, and then to take n large. You really could imagine repeating that for the case of it. Another done would be to write the so-called geometric form of the equation. So throughout, I've described this parameterization where what you put into the TBA equations is this complex curve, Z of sigma or W of sigma. And of course, it would be nice if the input were directly the boundary curve X of sigma or the cross ratios. And let me just say that this in principle can be still probably that of an actual research problem, but it's a very concrete, it's something which has a concrete way. Okay, so finally, let me just mention that there are a few topics that I wasn't able to discuss, which people in the audience might be interested in, and I'll invite you to ask questions about it. One is really the connection with the theta function solutions of Martin Krzyzewski and his class, which have a nice connection with this continuum TVA. And another is the details of this process of analytically continuing these TVA equations and the connection there with this topic of wall crossing and bootstrapping S matrices. So I'll conclude there.
Thank you, John. Now questions. We have 2 hours for questions. Till the public talk.
Can you do numerics as well with this equation?
Yes. So I actually have some slides that I moved from a previous. So the problem of computing these equations numerically is really just a problem. So the way it's generally done is that you start by making some zero-order approximation of your y function just by approximating it as its asymptote. Okay, and you plug that in to the right-hand side, you iterate it, you get some updated function, you plug it into the right-hand side, you iterate it, and you wait till it converges so that the iterations don't change the way. So that numerical problem just amounts to being able to do these integrals efficiently. Okay, so you need to be able to do integrals of this form efficiently. So let me say the theta integral. I should thank Ronald Yannick for teaching me while at the mathematical school in Brazil a few years ago. He taught us, many of us, how to efficiently do these sorts of convolution integrals in mathematics, which is to use the fast Fourier transform algorithms, which essentially turn the theta integration just into matrix multiplication, which can be done. The mathematical package does it extremely efficiently, somewhat of a black box. But it basically makes this theta integral true. So then there's the issue left of doing these tau integrals. So these tau variables are compact variables, so all you need to do is to expand this function f in modes. So you Fourier expand f. That allows you to do these integrals once and for all, and so at the end of the day, it also just becomes matrix multiplication in each step of the iteration. So basically, at the end of the day, using Fourier techniques, you can convert this integral just strictly to matrix multiplication. Okay, and so this plot here is the black dots are the area evaluated on the y function for each iteration of the TVA, and you can see it converging nicely to some number. I won't abuse the fact that this question is left when I have this slide, but let me just say that the blue line is actually the value obtained by actually directly brute force solving the equations of motion. So you can see it agrees quite nicely.
Can you show once more the final result, continuous TVA? Yeah. So here, this omega enters only in terms of z equal only. So omega is the shape of the contour. Enters through z only.
Yes.
And there is no Jacobian to this.
Copies.
I mean, Jacobians is like integration of t tau 1, t 2 tau. There is no Jacobians, there nothing. So the only input is of omega is in z. Is correct?
It's hard to tell this, you're echoing somehow.
So, omega
Yes.
is shape of the contour. It's your real input.
Yes.
It enters only through z, and that's all. Does it enter only through z?
I think it's confusing between omega and space-time.
So this z of sigma, you understand, is just a unit circle.
No, I mean, the real input is the shape on the right hand side, omega is sigma. This is your real input.
No, so
This is x, that's an x
but
minus.
you understand that neither of these curves is the physical boundary.
It's not physical. I mean, it has some. boundary in your z-plane.
That's right, yes.
Yeah, okay, anyway, so you specify this as omega.
Yes, you put this in, so for example, you could choose any shape you like.
Right, and you put it back in this equation z.
Yes, so the relate, of course, z sigma 1, sigma 2, which is this integral in omega coordinates, is just the difference, it's just the distance between these points.
So the question was, is it only the place where it happens?
Is it the only place where it happens? Is it the only place where love happens?
It enters here and then the phases.
Okay.
So in the omega plane, this phase difference is really the angle between these two lines.
Okay, so the next question is, can you make what omega corresponds to one polygon?
Yeah, so again, when you blow this curve out to infinity,
It's a square. Can you make hexagon?
Yes, thank you. It gives you the null square. So this comes back to the fact that we've only here, maybe I kind of pulled a fast one on you, but you caught me. So here we draw this picture with adding these residual yellow zeros inside and outside. Okay. But then I sneakily, or not so sneakily, just ended up adding them outside. Okay, so I've only added these yellow zeros outside. So this parameterizes a huge family of solutions. Okay. My guess is that it parameterizes exactly the family of solutions which can be solved in terms of theta functions. But one can also imagine adding these yellow zeros inside. Okay, but this will affect the connectivity of this diagram. Okay, so it will affect this term here. It will affect these integrals. It will affect this intersection matrix. But it will affect it in a way which you more or less know how it will work. Inside, there'll still be some cycles. So here I said outside, you can ignore the cycles related to these yellow zeros because they become in. So if you leave the zeros inside, you can no longer ignore those cycles. Okay, so you'll have some like residual piece of the old TBA left over. So you'll still have cycles associated with those zeros. And so the corresponding y functions appearing in this form coupled with the TBA. Okay. So in that case, when you take, then once you have this curve, so okay, then in this picture you'll have some yellow zeros inside. Okay. So you can imagine there blowing the curve out and you'll get some regular, well, not regular, so you'll get some polygon number of cuffs related to the number of zeros that you can see. If you want to map to the W plane, you can still do it, but this curve in the W plane will now intersect itself. So for example, if you have 2 zeros, if you leave 2 zeros inside, when you map to the W plane, it will map to a picture that kind of looks like this. Is mapping you have an interesting open problem.
Here. Can you comment about this relation with the Martin's solution?
Yeah, so this is something I had a slide here, but didn't have a chance to. So there is this whole technique of constructing solutions of the equations of motion in ADS using theta functions. Okay, so theta functions are basically just constructed like this. You have some Riemann surface, you construct a special basis of cycles on this Riemann surface, and this matrix, which is basically a matrix built from these cycles, and you make this theta function, which is this sum. So basically, using these theta functions, again, you can construct solutions to the equations of motion, and in the end, you can really construct the analog of y functions. So these theta hats are really just these independent shifts. And you can check that, that this big scary function actually satisfies the Euclidean generalization. So actually, Euclidean case here, so this would satisfy the Euclidean generalization of the TBA. Although recently it's also been worked out how to construct these theta function solutions in the Minkowskian case too, but I haven't checked yet that those Minkowskian solutions actually satisfy the TBA. Let me just make a note for people familiar with this this work of Martin and his collaborators, that you of course, when you go to these R22 invariant coordinates, in the Minkowskian case, you end up with a problem like this. Well, let me write FFR. You need to solve a problem like this. This is the Kullmeier reduced equations of motion. This f is some generic function. So in Martin's original theta function papers, what he does is he sets f to 1. Okay, so he basically saying he performs the control transformation whose Jacobian cancels this thing f, which is equivalent to setting f to 1. Okay, and then he finds some solution to this equation where, in terms of these theta functions, it's something like e to the 2 alpha theta z bar. And so what you can find is that this solution, this function here diverges along some contour in the complex plane. W sigma. So you find there's some finite region of the complex plane which is mapping to your world sheet. Okay, so when you put in a picture, this is really mapping to your x sigma and here. And this W sigma is precisely the W sigma that I mentioned earlier. It's really precisely this W sigma. So this fact that you perform the conformal transformation to set this f equal to 1 is exactly equivalent to the assumption that is inside this region. Okay, so that you can perform this conformal transformation. And then this W sigma just parameterizes the boundary of your world sheet. So it's exactly what happens here. You have this alpha, which is lives inside of some region bounded by this W sigma. And the boundary of this region maps to the boundary of space. So that's basically the connection.
No? No instructions class today?
Just a small announcement, please, related